Okay, so now I'd like to continue the previous example of our baseball, which is on a parabolic free fall trajectory. And I'd like to enrich that example. And we'll enrich it by introducing the force that's acting on the baseball. So as it moves, we're ignoring air resistance. As it moves, the only force acting on it is a constant force of gravity, constant in magnitude, mg, and constant in direction, always pointing down. At every point along its trajectory, there's a constant force acting, the force of gravity. And so this will allow us to do two things. One, we'll talk a little bit about how that force affects the motion, how it changes the velocity, the magnitude and direction. And this really gets at the heart of dynamics, okay, which is really what this course is about, is dynamics, F equals ma. And it will really allow us to sort of review sort of quickly the main step forward that Newton took, which essentially allowed him to unify the heavens and the earth and explain the orbits of the planets around the sun. And it's, the heart of dynamics. The second thing it will allow us to do is introduce a technical thing, which is the vector dot product. So the dot product between two vectors resulting in a scalar, and how this dot product plays a super important role in all kinds of physics calculations: kinematics, dynamics, energy, work, power, all that kind of stuff. Okay, so let's go back to Newton and the basics of dynamics. So the idea is, if you take a rock and you throw that rock in empty space, there's no objects around exerting gravitational forces. There are no forces acting on the object. And so the object's velocity is constant. That means it will move along a straight line with constant speed forever. It will just drift through space forever. Okay, so its trajectory will look something like this. Just a straight line through space with a constant velocity. Okay, so that's not surprising. Okay, we don't really need to explain that. Okay, so we just throw it and it just drifts forever. What we do need to explain, though, is if there are changes to its motion, a change to its velocity, which could be a change to the magnitude of the velocity, its speed, or a change to the direction of its velocity. Okay, it's no longer moving along a straight line. It's moving along a curved line. Okay, so suppose you're observing this rock floating through space, and you observe that, mysteriously, it's starting to speed up, move faster and faster. Okay, so you immediately conclude, there must be a force in a direction that is parallel. So two lines that are drawn parallel indicates a force in a direction parallel to the velocity. Okay, and that force doesn't change the direction. It just pushes, it keeps the particle moving in the same direction, but it increases its speed. It's moving faster and faster and faster. Okay? Or suppose, the rock is drifting along, and then you notice, hey, wait a minute, it's slowing down. Something's changing about its motion. Its speed is decreasing. Same direction, but its speed is decreasing. Well, you immediately conclude, there must be a force pulling back on the rock. So a force in the, let's say, negative parallel direction. So anti-parallel direction, anti-parallel to the velocity vector. Okay? So it's pulling back. So that force pulling back on the rock is not changing its direction. The rock still moves along that straight line, but the speed of the rock is being reduced. The magnitude of the velocity vector is getting smaller and smaller. Okay, so forces in the direction of motion increase the speed. Forces anti-parallel, or in the opposite direction of the motion, decrease the speed, but have no effect on the direction of motion. Okay, but now suppose you observe that this rock is going along, and then it continues to move with constant speed, but whoa, its direction is changing. It's starting to move on a curved path. Well, force in that direction increases the speed, force in that direction decreases the speed. Neither of them change the direction. It must be that a force perpendicular to the motion. So in this direction. So this symbol here with a horizontal line and a vertical indicates perpendicular force. In this case, the force perpendicular to the direction of the velocity. So a force in this direction won't change the speed, but it will change the direction of the motion. Okay, and so the particle will start to move on a curved path. And of course, this was the secret. This was the huge discovery, the huge breakthrough that I said unified the heavens and the earth. One of the single most important steps forward in the history of science was because then Newton could say, oh yes, we have these planets moving on basically circular orbits or elliptical or whatever, basically circular orbits, say the moon moving around the Earth. Okay, so here's the Earth and here's the moon moving in its circular orbit around the Earth. Okay, and Newton realized that to move in a circular path like this, it requires not a force in the direction of motion, but a force perpendicular to the motion, directed right towards the Earth. And then, well, what could that force possibly be? Well, we know that when we're standing here on the Earth and we drop objects, those objects fall towards the center. Okay, you can feel, it seems like there's a force pulling objects down. Maybe, just maybe, that force of gravity, extends not only just to the tops of mountains on the Earth, but extends way out and reaches up to the moon. And so then this massive object here, the Earth, exerts a force on the moon perpendicular to its motion. At this instant of time, it's moving that way. There's a force perpendicular to that motion. That's not changing the speed, it's changing the direction of the motion. And then the moon just goes around and around under that centripetal or center-directed force causing its circular motion. Okay, so prior to that, everyone thought, oh, well, to move in this circular orbit, you need a force pushing it around. Well, that's not the case. It's perpetual motion. This thing would just drift forever with constant speed along that straight line. Perpendicular force, constant speed now along a curved path, a circle around. Okay, and so that was a huge step forward. And this is the central point of dynamics. Okay, so really what we're interested in physics is when forces act on objects, we are interested in the components of the force parallel to the motion, which change the speed, increase or decrease the speed, and components of the force, or the component of the force perpendicular to the motion, which change the direction but don't affect the speed. Those are the two things that we really need to sort of think about. So let's apply this, think about this in the context of our baseball on its free fall parabolic trajectory. So let me just redraw a portion of our baseball's trajectory. So like this. Okay, so for example, suppose it's on this point of its trajectory. Well, then its velocity. Velocity is always tangential to the trajectory. It's of some magnitude and it's tangential. Okay, so this will be the velocity at this instant of time on its trajectory. And then it'll go higher and higher, slow down, change direction, and then start speeding up, changing direction all the while. So when it's at this point in its trajectory, its velocity is in that direction. Okay? And so now all along its trajectory, at every single point in time, there is a constant force acting, which is the force of gravity. That force of gravity points straight down towards the center of the Earth and has a magnitude mg. Okay, so we'll just call that force F, and there's exactly the same force of gravity pulling down at this point. It's a constant force that's acting, causing a constant acceleration, an acceleration in that direction at all times. Okay, and now when we think about this, sure, you can split this force into x and y components, but that's not very useful. It's not very conceptually clear what's happening. To make it clear, the effect that this force is having on that velocity in terms of its direction, magnitude and direction, you need to split this force vector into two components, one parallel to the motion and one perpendicular to the motion. Okay, and so we can say, well, here's a component of the force perpendicular, and here's the component parallel. So here's the force component perpendicular. The component of F perpendicular to the velocity v is this. The component of force that's parallel to the velocity, in this case it's anti-parallel, okay, in the opposite direction of the velocity, that's this one. We won't say negative parallel, we'll just say F parallel. Could be negative or positive. Okay, so that's great. So this component of the force, this changes the direction of the velocity vector. This is the component of force that makes the moon curve its trajectory. This is the component of force that makes the parabolic trajectory bend over like this. Okay, and then there's a component of force also parallel to the motion, in this case pulling back, exactly opposite to the direction of motion. This component of the force changes the speed. In this case, it reduces the speed. Changes the speed of the motion. Speed, magnitude of the velocity, or direction of the velocity. Okay? And changes the speed. In this case, it reduces the speed. Okay, great. And then we come, so then at this point, the direction is changing. It used to be this way. Next second it'll be here, this way, this way, this way, this way. So this component of the force is rotating the direction of the velocity vector from this direction later on to this direction. It rotated. Okay? And this component of the force is reducing the speed as it goes up and up and up. At this point, the force is in that direction. It is only a component perpendicular to the motion. Motion is that way, force is that way. There is no component parallel to the motion, so the speed is momentarily constant here and a minimum. Okay, and then when we enter this half of the trajectory, say we're at this point over here, again, we can split f into x and y components. Who cares? What we really care about is the component of the force in the direction of motion. So in this case, that's this. So this would be F parallel to the motion. In this case, it's a parallel as opposed to anti-parallel, and a component perpendicular to the motion. So here is F perpendicular. Okay, so again, same as before. The parallel component of the force changes the direction of the velocity vector, and that's what makes the trajectory not a straight line, makes the trajectory curve. The perpendicular component, so this changes direction, and this changes direction in both cases. Along the entire trajectory, the perpendicular component is always bending, is always rotating the velocity vector, its direction of motion. Okay, and then this component of the force, F parallel, so this component changes the speed or the magnitude of the velocity. In this case, it is increasing the speed. So on the way up, the speed is ever decreasing, slower, 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 reaches minimum speed here, and then the speed ever more increases on the second half of its trajectory. Okay, so the point is that that what we are really interested in is not the xy components of the force, but the components of the force parallel and perpendicular to the velocity. Okay, so how do we do that? Well, what I'm going to do is I'm going to take this part of the diagram, and I'm just going to blow it up here a little bit and put it down here. So here is a part of the trajectory, and this point here is this point, and, well, I don't know if that's really going to help drawing it down here. Let me draw it a little bit bigger. Let me draw it a little bit bigger in this little part of the board. Okay, so we're coming up here like this. This point is this point. This is the velocity at that instant of time. This is the force at that instant of time. Okay, and we're going to take that force and we're going to split it into a component that's perpendicular and a component that's parallel to the velocity. Okay, great. And so what we really want to do is we want to figure out what is, first we'll use the vector dot product to figure out the component of force parallel to the motion, and then we'll use a bit of algebra then to figure out the component of the force perpendicular. And so let's put in some numbers here. So we have from a previous example, the velocity was 4 in the I hat plus 3 in the j hat meters per second. So this is in terms of x and y components. Or in terms of speed and direction, it's 5 meters per second. That's the magnitude of that vector at 37 degrees. And remember, all directions are counterclockwise relative to the horizontal, to the right direction. Okay? And let's also give the we've given the velocity a particular magnitude and direction. We'll also give the force of gravity a particular magnitude and direction. So the magnitude is just mg. I don't care what m is, I don't care what g is. Let's suppose that mg is 10. Okay, so it'll be 10 newtons is the magnitude. Okay, and to get the direction right, we say negative j hat. So the force of gravity is negative 10 j hat newtons. Okay, we just pulled this number out of our head, just a simple round kind of number. Okay, now what we're going to need, and this is very important, we're going to need a vector in order to figure out the component of the force that's parallel to the motion. In order to compute F parallel, we're going to need a vector that is in the direction of the velocity vector, but that is of length 1. So instead of calling it v with a vector symbol on top, we'll call it v with a hat on top. So the hat is just like I hat, j hat, k hat. Those are dimensionless unit vectors. They are vectors of length 1 that have no dimensions. So we need to figure out that vector. Okay? And so the way that you do that, and maybe I'll do this down here, make use of the space here because we're kind of limited. So let's do that down here. So we define v. So how would we sensibly do this? Well, we would take the vector v and we would divide by its magnitude. So, or multiply by 1 over its magnitude. You can take a vector and you can multiply or divide by a scalar quantity and you'll end up with a vector. And so what we do is we start with the full vector v and we simply divide by the magnitude of v, its length. And so if you take a vector and divide by its length, well, you're going to end up with a vector of length 1. This is of length 1 here. Okay? And so I guess we should work this out. So this is, well, I should say what it is. So this is a dimensionless, 2 important properties. It's dimensionless. It has no dimensions. It's not meters per second. And that's because the vector in the numerator has dimensions of length over time, or units meters per second. The speed also has dimensions length over time, or units meters per second. When you go meters per second divided by meters per second, you end up with something dimensionless. So you'll get a dimensionless vector, and it will also be a unit vector. Okay, and then it is in the direction of v. It's exactly what we want. Okay, so let's just work this out. So what we do is we take the vector v. Let's use I hat, j hat components first. So we go 4i hat plus 3j hat meters per second. That's the vector v. We divide by its magnitude. Oh, its magnitude is 5 meters per second. You'll notice that the meters per second in the numerator cancel the meters per second in the denominator, and so you have a dimensionless vector. Okay, and what is it actually? So it's 4 divided by 5 is 0.8 in the I hat direction. 3 divided by 5 is 0.6, so plus 0.6 j hat, and it's dimensionless. Okay, you can also write this as the vector itself is 5 meters per second at 37 degrees. If you divide by 5 meters per second, you just get 1 at 37 degrees. This is 1 at 37 degrees. So this is dimensionless. Okay, very good. So that's that. And now I should say something just very important here, is just sort of to round this out. And this is just a general thing to keep in mind. Okay, so you have a vector, any vector, in this case the velocity vector v. You have a symbol with a vector symbol on top. Okay, so that means a vector. It has magnitude and direction. And so the magnitude of it is indicated, take the same letter, but don't put anything on top of it. Just the letter by itself indicates the magnitude of that vector. And then there's another thing you can write down, which is the direction of the vector, a unit vector in the direction of the vector v. These 3 things, 1, 2, 3, all of these are different things. Learn to distinguish between them. Get careful with your vector notation and really get familiar with it, because by the time you get to second year, you're going to know this stuff like the back of your hand. Okay, so use this course, 121, this intro course, to get really familiar with vectors and vector notation. This is the original vector, this is its magnitude, and this is its direction, a unit vector in the direction of the original vector. Each of these things are different things, okay? So keep that in mind. All right, so now let's remind you about the dot product. So I'm assuming that you've talked about the dot product either in the vector dot product, either in your high school physics course or a math course or whatever. So I'm just going to quickly remind you what that is. And so what we have is, I'm going to run out of room here, maybe. So what we have here is a vector, an arbitrary vector A in 3-dimensional space pointing in that direction, and an arbitrary vector B in 3-dimensional space pointing in some other direction. It could be that way or whatever. It's easy to draw the diagram like this. And there's an angle theta in between those 2 vectors. And the vector dot product is defined as you write the vector A and you write the vector B and you put a dot in between them. It's called the dot product. And this is a way of converting two vectors into a scalar quantity, so just a number. Okay, and so this is defined as the magnitude of the first vector, which is the letter A without a vector or without a little hat on top of it, times the magnitude of the second vector. Okay, that's the B without a vector symbol and without a hat on top of it. Magnitude of the first times the magnitude of the second times cosine of the angle theta in between those two vectors. And you can see that there are three sort of critical cases here that you can think about. So in the case that the two vectors are parallel, okay, so that means that the angle between them is 0, cosine of 0 is 1. Okay, so that means, and A and B are always positive quantities, okay, or 0. Okay, just assume that they're not 0, they're positive. So this is going to be greater than 0, okay, if theta is either 0 or all the way up to 90 degrees. So if theta is less than 90 degrees, so between 0 and 90 degrees, A and B are, generally speaking, parallel. They're generally speaking in the same sort of direction-ish. Okay, then the dot product is positive. If you crank the angle up to 90 degrees, so the case that theta is equal to 90 degrees, cosine of 90 degrees is 0, and it tells you the dot product is 0. So when B is perpendicular to A, and then the dot product is 0. And so that's great. So that allows you to tell when the dot product is super useful to tell when two vectors are perpendicular to each other. Okay, and then the other case is if this is an acute angle between 0 and 90 degrees. If you're greater than 90 degrees between 90 and 180, then theta is, let's say, greater than 90 degrees. And that's an obtuse angle. In that case, the vector dot cosine of that angle greater than 90 degrees is negative. And so your dot product will be negative. So when you look at a dot product between two vectors and you see it's positive, then they're generally in the same sort of direction. They might be exactly parallel, but they're generally in the same direction. If the dot product is negative, they're generally pointing in opposite directions. If the dot product is 0, they're exactly perpendicular, okay? Or one of them is 0. Okay, great. And one other thing to say about the dot product is, generally speaking, you know that if you have an I hat, j hat coordinate system, or k hat, if you want to go in 3 dimensions, that's not very nice, I hat, j hat, you can always take any vector and you can split it into I hat and j hat components. You can write any vector as a linear combination of I hat and j hat components, and so you need to know the dot product between I hat and I hat and I hat and j hat and I hat and k hat and so on, but that's easy to work out. So I hat dot I hat, so what's that? According to this definition, it's the magnitude of the first, well that's 1, because these are both unit vectors, times the magnitude of the second, well that's also 1, times cosine of the angle between them, well they're both exactly the same direction, so the angle between them is 0, and cosine of 0 degrees is 1. And so this is 1. Okay, or say I hat dot j hat. So that'll be the magnitude of I hat, that's 1, times the magnitude of j hat, that's 1, times cosine of the angle between them. Well, I hat and j hat, the angle between them is 90 degrees, cosine of 90 is 0, and so this is 0. And that's obvious because I hat and j hat are perpendicular, and the dot product of perpendicular vectors is 0. And similarly for I hat dot k hat and all the other possible combinations that you can come across. Okay? So now what we want to do is we want to apply this little tool here, this little definition of dot product, and you're going to see how useful it is. In particular, it's super useful for determining the component of any given vector, in this case the force vector v, the component of that vector in the direction parallel to any other vector. I guess we should be thinking about this diagram. The component of the vector f in the direction of any other vector, let's say v hat here. Okay, so what we're going to figure out is what is this f parallel. Okay, so how do we do this? So what I want to do is just write down something and we're going to look at it. Okay, so we're going to take the vector f here and we're going to vector dot product with the unit vector in the direction of the velocity. And we'll see what happens. Okay, unit vectors, dimensionless unit vectors always have a caret or a hat on top of them. Okay, so let's work this out. According to the definition of the dot product, we take the magnitude of the first vector, which is the symbol f without a vector or without a hat, times the magnitude of this vector, well that's a unit vector, so that's just 1, okay, times cosine of the angle in between them. Well, what's the angle in between them? Well, get rid of that 1 there. The angle between them, f, this is f, this is v hat, the angle between them is theta. Okay? Now, we're going to take one more step here to make it completely obvious what this is. We're going to say, let's not look at this angle theta, let's look at this complementary angle, which is, we'll call theta star, just to distinguish it from theta. And you'll notice that theta plus theta star adds up to 180 degrees. So theta star is 180, or pi, minus theta. And cosine of theta, if you think about it for a second, cosine of theta is the negative of the cosine of theta star, because you flip from, say, the first quadrant to the second quadrant. And so the cosine, the sign of the cosine switches. So this is the same as negative f times cosine of theta star. So incidentally, I'm assuming that you guys are familiar with basic trig and can think about things like that. Okay, if you're not, you should just go back through some of your trig stuff. This trig stuff is super important. Sines, cosines, tangents, angles, when you have a right triangle, all that kind of stuff. I'm assuming that you guys know how to do that, are comfortable with that. Okay, and so this is the projection. It's a very important word. This is the projection, this guy right here, negative f cos theta star, is the projection of the vector f along this line. It really is this, okay? And so you can see that if you look at f, ignore the minus sign, f cos theta star, well, what is this? Well, this is a right triangle here. There's the 90 degrees. This is the hypotenuse. The hypotenuse times cosine of this angle is the magnitude of this side of the triangle. Okay, that's what this thing is. But wait, there's a minus sign in there, so the dot product even takes care of the minus sign for you. It tells you that, yeah, the projection of f along the direction of v hat has this magnitude, and there's a minus sign telling you that it's in this direction, not that direction. It's anti-parallel to the velocity. Okay, so that sign is very important. Okay, and the dot product automatically gets that right for you. Okay, great, awesome. So this will allow us to figure out what f parallel is. Okay, so now let's actually work it out as just algebraically. So we'll take the vector f. So what was that? The vector f was negative 10 j hat, and then the units, newtons, vector dot product with a unit vector in the direction of the velocity. What was that? That was, this board is full, down here. Okay, so a unit vector in the direction of the velocity is 0.8 I hat plus 0.6 j hat, okay, dimensionless, okay? And so now you can work this out. So you just work this out term by term. J hat dot I hat, oh, they're perpendicular, that's 0. J hat dot j hat, oh, well, that's just 1. Okay, and so what you get is negative 10 times 6 is negative 6. And then the units are newtons. So this tells you that the projection of the force F, it has a magnitude 10 straight down. Its projection onto the direction of the velocity is negative 6 newtons. So this is a magnitude 6 opposite to the direction of the velocity. That's 10, that's 6. Okay, great. Then what shall we do? Then we'll actually write down what F parallel is. Okay? So F parallel, okay, so we know it's negative 6 newtons, okay, and in which direction? It's negative 6 newtons in that direction, in the v hat direction. Multiplying by v hat doesn't change the length, because v hat has length 1. It doesn't change the dimensions, because v hat is dimensionless. So this is still a force vector. It's negative 6 newtons in the v hat direction. So we can just work this out algebraically. This is negative 6 newtons. Okay, just times v hat. V hat is this, 0.8 I hat plus 0.6 j hat. Okay, and so we work this out. I'm going to run out of space here. So this is 6 times 8 is 48. So this is negative 4.8 in the I hat direction. Negative 6 times 6 is negative 36. Negative 3.6 j hat. And the units are newtons. Okay, and then you can just double check. Have I made a sign error somewhere? So this right here is this vector. it has I hat component that's negative and j hat that's negative. That's right. The I hat component is negative. The j hat component is also negative. So they're both negative. It's telling you it's in the third quadrant or whatever you want to say. Okay, so there you go. And that force vector, that component of the force vector pulls straight back on the particle, reducing its speed but not changing its direction. Now we want to figure out, now that we know this and this, we can now figure out F perpendicular. So F perpendicular, we know that F, the full vector F, is equal to F parallel plus F perpendicular. F parallel plus F perpendicular. That implies, so a double line with an arrow means, logically implies, that the component of the force perpendicular to the motion is just the full force F minus the component parallel. We know that, and we can do this calculation. And just remember that subtracting a vector is the same as adding its negative. So this is the same as F plus the negative of F parallel. Okay, so let's go back to our diagram. This is F parallel. This is the negative of F parallel. Okay, it's of exactly the same magnitude, but exactly the opposite direction. And so what this says is to calculate F perpendicular, we need to start with F, and we need to add the negative of F parallel. We need to take that vector and add that vector. And you can just do this graphically, just tip to tail. You can take this vector, start with F, and then add this vector tip to tail, bring this vector down to here, and you'll see, oh yeah, look. This vector right here is negative F parallel. So F added to negative F parallel gives you this resultant vector, which is F perpendicular. Okay? And I suppose that we could just crank it out sort of algebraically. So let's do this. So F was negative 10 j hat newtons, and then the negative of F parallel was this thing. So the negative of F parallel, so we add the negative of this, both of those negative signs become positive. So it's positive 4.8 I hat, positive 3.6 j hat, and this is also newtons. And so we end up with negative 10 plus 4.8 is 5. Oh, sorry, that's j hat. Okay, so there's only one I hat component here, and so this is positive 4.8. So it's the I hat from this is nothing, plus the I hat from this is 4.8 in the I hat direction. And in the j hat direction, we have negative 10 plus 3.6 is 6.4, negative 6.4. And that's newtons. Okay, and then you look and you say, well, does that make sense? Did I get this right? So we're calculating F perpendicular, and F, this is F perpendicular. So we have F perpendicular, is this right? It's saying it has a positive I hat component, okay, and that's right. This vector has a positive I hat component and a negative j hat component, positive, negative, okay, and so that's right. Okay, great. So now, let me do sort of one last thing here, which shows you how useful this is. Okay, I think we might be able to squeeze it down here. So what we do is we define power. So P is power. So power is the rate at which energy is being transferred to this object. Okay, so this object has some kinetic energy, it's in motion, and the power that we're going to calculate is the rate at which its kinetic energy is changing. So we'll go through this in more detail in later lectures, but it's the rate at which the kinetic energy is changing. A change in the kinetic energy is energy transferred. So that's work done. Okay, and so you know that work done is vector force, vector dot product displacement. Okay, so when you're calculating work, it's always a dot product, a vector dot product. Okay, and then divided by delta t. And so you can pull the force vector out. This is force dot delta r delta t. This is the rate at which the position vector is changing. Well, that's the velocity. Okay, so we will definitely talk about this in more detail a little bit later, but power, the rate at which kinetic energy is being transferred to this object, okay, is the force that's acting on the object, gravity, vector dot product with the velocity of the object. Okay, for a given force, bigger velocity means the bigger rate at which kinetic energy is being transferred. Okay, so it's the vector dot product of force and velocity. Okay, so let's so let's just work this out. So what is the force? So the force is negative 10 j hat newtons. Vector dot product with the velocity vector. The velocity vector is 4I hat plus 3j hat. 4I hat plus 3j hat meters per second. Okay, and so then the power, P, the rate at which energy is being transferred to this object, is going to be j hat dot I hat is 0. J hat dot j hat is 1, so you have 3 times negative 10 is negative 30. You get a scalar out of a dot product. Okay, and the units are newtons times meters per second. So Newton meters per second. Great. And remember, Newton meters, that's like force times distance, is energy, is joules. Okay, so this is negative 30 joules per second. And joules per second is a rate at which energy is being transferred. So and so many joules per second. Well, that's watts. So this is negative 30 watts. Okay. So this is just a simple example of how dot product is used everywhere. Okay. So we want to calculate the power, the rate at which the gravitational force is transferring energy, kinetic energy to this object. We take the dot product and we get negative 30 watts. That means the gravitational field is, removing 30 joules of kinetic energy per second. So, because this is on the upward swing of its trajectory, its speed is decreasing, its kinetic energy is decreasing, and that kinetic energy is going into the gravitational field. Okay, and so the gravitational field is delivering energy to this object at a rate of negative 30 joules per second. Okay, so yeah. Another way to work out this power, you can just work out the power directly. You can say, well, the power is, equal to, instead of doing I hat and j hat components, you could just say, well, the power is the parallel component is F dot V. So F is force parallel plus force perpendicular, vector dot product V. The component of the force perpendicular to the velocity is 0, so F perpendicular dot V is 0, and so you're just left with F parallel vector dot product with V. So it's just this thing times this thing. And F parallel, the magnitude of F parallel, we worked out, what was the magnitude of F parallel? 6 newtons, and the magnitude of V is 5, so 5 times 6 is 30, and you get the same answer here. Okay, so that's very good. So this was so the whole point here is, just getting back, the whole point was the central aspect of dynamics, which is the central point of this course, is to get across the idea that you don't need to explain uniform motion. What you need to explain is changes in motion. And changes in motion or accelerations are caused by forces. And what you're really interested in is, if you have some motion in some direction, you're interested in how the force that's acting on it changes that motion. Components of force, parallel or anti-parallel, change the speed of the velocity, change the magnitude of the velocity, change its speed. Components of force perpendicular to the motion don't affect the speed, but change the direction of motion. And so what we really need to sort of understand technically is, how you do this, how you take a force, a given force, and split it into components perpendicular and parallel to the motion. And a really good tool for doing that is the vector dot product. Okay, and the vector dot product is hugely useful in all kinds of things in this course and in physics in general. All right,